Hi everyone. Today I'm going to introduce our optimized analytics platform for Spark platform. Yeah, and I'm Daoyuan from Intel, and my co-speaker is Yuanjian from Baidu. He's Baidu's Spark team leader, and so in big data area we have 4V definition here, and today we are focusing on the velocity of the big data area, because even though people are querying data on larger data sets, they always want the query execution to be as fast as possible. And also, some approach may trying to pre-compute some results and put them in somewhere so that later queries can benefit from those pre-computed queries. But as those pre-computed results may conducted daily or weekly or hourly, so those new coming data could be still be very slow. So we want those new coming data to run as soon as possible. And according to a survey conducted by Databricks, we can see that over 90% of people are focusing on the Spark's performance. So performance really counts for our applications. And for Intel, we also are providing many new technologies like 3D Point. Here we now have Opton SSD coming into the market. So we are now having a larger storage with faster access there. So how do we optimize these technologies to optimize our applications to fully utilize them? We'll take care of this in our packages here. So here comes the whole blueprint of our package app. App previously has a code name of Spinach. That's a vegetable. And in Spinach, we are providing some user-defined index here, and we also provide a fine-grained cache down there in the cache layer, so we can store the cache in the memory or in the 3D Point devices. And also we have indexed data source and cache-aware system, so the Spark scheduler could know where the data cache and indexes are located, so the scheduler could be even more smarter. And we can use other Intel's technology like RDMA, QAT, or ISAL, FPGA to accelerate the whole query execution. So this is, I'll introduce our OAP's advantages here. We are open source project here, so it's free to use, and we can make full use of your current hardware. You don't have to buy any Intel's device specifically for this. You can use any system that's compatible with Spark. Yeah, and we have good performance since we are adopting the traditional database indexing system like B-tree and bitmap there, and we can see 5 times boost compared to the original Spark. And since it's as easy as a Spark package, so it's easy to deploy and maintain. And also the queries there is just the same to the old ones. The system would automatically see if we can benefit from the existing indexes and do those things transparent to developers. So it's also very easy to use. Okay, this is brief case for our app cases. You just start Spark as you always do, whatever you like. So you can start a Swift server, you can start a Spark SQL share or Spark share, or using your data frame API to create any applications there. Just specify app as your dependency there so that app's classes are in your class path. And then you can create table with Spinach format, or create a table using Parquet or any other file format that app package has already supported. Then we extend the Spark SQL DDL so the user can define their own index there. We use the word syntax because to define that the index is different from the Hive index system. And it's a Spinach index, so we use the abbreviation of S-index. And now we are supporting B-tree and bitmap. After inserting data, you can just run your query. The data scientists could focus exclusively on their data science things, so you don't have to matter. Since they are using the column A as a filter here, we see that we have a corresponding index to optimize this query, and this query would be automatically optimized. So how do we do this? We are storing 3 types of files in the storage system. Like we are using meta file and index files and data files to handle all of this. The data files look much more like Parquet's data file, but we are providing row groups, and inside each row group, we have multiple columns according to the defined table schema. And for each column, we call that data fiber. And for indexes, the index files are one-to-one according to your data files, so that when the data updates, you don't have to change the existing index files. And here, the index files consist of statistics data and index data. The index data are considered as index fiber there. So the fiber would be treated as a minimum cache unit for the whole cache system I'll mention later. And then when the query comes in, the Spark would do predicate pushdown for us. Here we can see that we get a filtered scan here, and inside up we would first refer to our metadata to see if there is any available index to accelerate the query here. If there is, we would check all the indexes matches to find the best one that can optimize the best for the query here. And then we read the statistic data to define that if this could really benefit the query. And then we can read the index fiber itself and cache them in the memory and get the row ID of the corresponding results. And then we just get the result here. Or we can fall back to the full table scan way to scan the whole data file there. And whatever you are accessing, the data file or the meta or the index file, they are all cached in our memory for now. Yeah. So we also build a compatible layer for Parquet. Since we are using our own file format just now, and well, many of those users have already get existing Parquet data. So we want to support existing Parquet data here, and we just build a compatible layer to also enable the reader with a given row ID to access a certain row group here and get the result I want. Yes, and since we have caches crossing the whole cluster, so for each executor, we have a fiber cache manager to manage all those caches. And the fiber cache manager will send what they cache to the driver-side object of fiber sensor. So the fiber sensor could update and maintain the whole map of the cache circumstance. And we did a little modification to the DAG scheduler. So the DAG scheduler would also refer to our fiber sensor to determine whether we want to schedule the task to which node. So the node could make more use of those already cached in memory data. Yes, and we do some draft benchmark in our lab. So we have 2 slave node cluster that's really small, but just for proof of concept. We generate 300 gigabyte data with that's compressed with gzip and stored in Parquet data. So the first column shows the Parquet vectorized read that's pretty close to original Spark does. And that takes more than 17 seconds to finish the whole query. But for our index read, we can see that the query time, we only use 7 seconds to finish that. And after several runs, we can see the cache system here just boost the query to merely 2 seconds. Yes, and then we can check some use case from Baidu, and Baidu and Intel co-developed this project. So, and they are our first user to try. So let's see how they use them. Yeah.
Hello. Okay. Thanks for Daoyuan's details introduction about Spinach, and currently they renamed it to OAP. And next, I will introduce some details of our work and some user cases in Baidu environment. First, a simple introduction of myself. I'm Yuanjian, come from Baidu infrastructure team. Our team is responsibility for the others business group for Baidu, like the search service group and the financial service group. Okay, first details about Spark in Baidu. We introduced Spark in 2014 and the version 0.8. 1 year later, we built our own standalone cluster and integrate with many others Baidu in-house, like file system, PubSub system, and DW systems. And as the year of 2016, we integrate with our own resource management and isolation systems and build our cluster over Yang. And as the year of this year, we have the platform of 6,800 nodes and about 5,800 jobs per day. Also, in this year, we dived into the Spark performance tuning, and also we cooperated with Intel with the OAP. So, with the rapidly development of Spark, we think about how can we bring more people, even though they are not developers, bring more people to enjoy the benefits brought by Spark. So, we implement ad hoc query service named Baidu Big Circle. You can see that the Baidu Big Circle consists of 3 layers: the API layers, the control layers, and the boosting layers. In the API layers, it includes the meta control API, like the project API and also table control API. And in the job API, load and export job mainly responsible for the data import and output. And the query job is just the Spark Circle query, but it's differently because of we can save our result to a temporary table. And in this way, user cannot through their result may be very big, very huge through the driver. It is one kind of the reduce the driver's overlap. And also the index control. Index control is mainly responsible for the OAP index creation and job. In the control layer, Big Circle Master responsible for the meta control, like some safety about and also some job schedule. And the worker is a customized Spark driver. And we have many Spark drivers in our cluster. And also we can classify the big query and small query. Just like the keynote, like Databricks guys in this morning. And we also meet the problems of big query and small query. I will introduce later in next slides. And also the core layer is our boosting layer. It is many reasons why it can run faster than the native Spark. And I also will introduce this in detail later. Okay, in our environment, we divided our resource into several load query queues and one query physical queues. You can find that a load job running on the load query queue, and also it reads data source from many kinds of data source like raw logs and our in-house DW. And the user starts their load job, or they just start by the scheduler, and it reads from the data source, save ETL work. After the work, they will save their result to a Parquet file, to many Parquet files. And each load job corresponding to a destination table's single partition. Each load job corresponding to a single partition. And also after the save, and we will call the BBS masters outer table API. So we can add a new partition for the destination table. From now on, the new coming data are visible to the people, and they can search it. And also, it still will start a background job and create the new partitions index. So you can see that the index is flexible. We can create index for each partition. And also, you can search it for each partition. Okay. You may see that we divided our query physical queue into 3 parts, and here we judged the query job. We classify our query job into 2 parts, the big query and the small query. Generally, the small query can complete in about half minutes, and we judge this in many dimensions like the job, the task numbers, the input-output data size, and also any other metrics we can get from Spark SQL. And also you may find that the ad hoc query cluster are faced to human beings. So how about the midnight? You will find that the queue of the query job runner is idle. So we solve this by integrate with the whole Spark over Yang to our resource management and isolation systems in Baidu in-house. And in this way, we can start other containers and to solve the idle problem. So next, I will give you an introductory story about Big Circle in our real world. And firstly, today is Mother's Day. I want to buy some flowers to my mother, and in China I will search it on Baidu, and these 2 Chinese words means flower. I will type flower onto our Baidu search box and click a button, and it will return some natural result and some advertised link. And if I want to buy some flowers, I will click one of the link, and the system will, in background, generate charge action to the advertisers. This is the simplest the advertisement systems scenario. And now, if I was a product manager of the advertisement system, maybe I want to know that how about the top 10 advertisers of the Mother's Day who pays much money triggered by the query word flower. Okay, it's not maybe an easy job from before Big Circle, because it's huge logs, raw logs, and also some data I need to join. You know that the click and the show of the advertisement should join together and find the final charge sums. So before Big Circle, maybe the product manager should find a developer like me or others, and maybe MapReduce job or anything others. But in Big Circle, you can, our product manager, most of them can write circle. So you can write a circle into our website and just click a button, and in this case, after about 12 seconds, you can see the result of the top 10 advertiser, and also a simple visualization charts. It's one kind of matte, right? So in the whole plan, we can find that we first build the index before user creates the search. And also we can use multi types of the index. Currently we support B+tree and also the bitmap. And also you can find we can have the 5 times faster than the native Spark and even 80 times faster than the MapReduce job. Our Baidu charging log have about 4 terabytes per day and about 7,000 files per day. All of these queries within 3 days, we can finish in 10 seconds to 15 seconds. So it's really a faster speed, and also it's really an ad hoc query service. So how can we make this, and why Big Circle can faster than the native Spark? Next, I will introduce some details about the boosting layers. First, we can see that the roll-up table layer. The roll-up table, maybe the concept is similar as the materialized views in OLAP systems. You can see that the table in our platform is very huge. The background is that, like I said before, we should join the click log and the check log together. So the table become huge, and most of them have about hundreds of columns. But 99% of users your queries, you can't see the hundreds of columns, you just maybe below 10 columns. So we solve this by build the multi-roll-up table based on the high-frequency columns. In this case, we built 2 roll-up tables. First roll-up by the user ID column, and the next by the Spinach column. All of these are user transparently. You can see that you just write the circle as before, and we can transparently change your circle and hit the roll-up table in the background. So in this way, we can solve the high-frequency queries in our scenario. But how about other general queries? It's on to OMP. We call it Spinach before. In this case, we can see that each data file corresponds to several index files. And in this case, we build index on the age column and also the department column. Age column use the B+tree search index, and the department column use bitmap index. You can see that in our build index, after our index build, when the query reached our systems, we firstly judge whether the query hits the index. If it's hit it, we first find the index file and check the columns and get the row ID in this query. And also, thanks for our skippable reader for the Parquet, and we can skippable read the data file. If it not hits the index, it's just like the same, and also the general as a native Spark, and read the data file. Okay. Also, as I mentioned before, each partition have their index file, and for example, if your query overlap about 5 partitions, 3 of them have index and 2 of them have no index, that's also okay. That's also no influence to your result. Also, with the hit index, during the hit index, we can also find that we read small pages in our Parquet file. Page is the smallest unit of Spark reading. And during this time, we can also catch them on the heap size, off-heap in our executor. And maybe next query or next query can hit the same block or same pages. In this way, we hope that it can boosting our queries further. And also, this feature was tested on our offline environment, and also maybe sometimes it's still some problems like frequency memory swap in and swap out. Currently the cache is not configurable by the column. So next we will also try to improve this. Okay. Also, Baidu has also some contribution works to the Spark community, and also during the development of Big Circle, we also find some improvements and also some bugs of native Spark, and we also try to contribute to Spark. Except some small bugs, and also many of them are the performance pruning, and also. In these days, we focus on the drivers bottlenecks, while the task number about over 20,000. The driver will be a bottleneck, and also sometimes it's very slow. So we may hope we can do more contribution works to the Spark community. Okay, as a last, we want to see some future plans of OAP, and also we cooperate with Intel. First, like I said before, the memory cache and the evict policy should be more smarter. And also, we are compatible with more data formats. Currently, we support two kinds of formats. First is Parquet, and the second is built-in Spinach file format. And also, we want to optimize more so-called operators with index. Currently, we may not support the join and the aggregations. So we will plan to fix this in later. And also, thanks for the Intel, they integrate more hard work technology into the OAP package, and maybe in some letters they will support the QAT authentic X point in the package. Also, our OAP has been open sourced, and welcome to all of us contribution. As a last, a simple advertisement for the women in big data. If you enjoy, you can join them. Okay, that's all of our talks. Thank you.